Hi guys, so today we'll be speaking about Wave SPM Form 5 Chapter 1. So my name is IMAN AL-QHALYDD PUTRA bin JEMADI and I'll be teaching you on the first topic of Form 5. However, note that this chapter does not involve too much calculation and basically we'll be speaking about facts and understanding on certain subtopics. So to move on, oscillation. Oscillation at an equilibrium is defined as position at a point where an oscillating object experiences zero resultant forces, which means this certain object does not move because no force acting or applied on it. Next is amplitude. Maximum amplitude of an object from its equilibrium position. The SI unit is meter. To understand this further, we'll refer to the graph later, and I'll show you where this amplitude is located. Next is frequency. So frequency is the number of oscillation that take place in 1 second. The SI unit is hertz. Or in other words, in 1 second, how many oscillations can be taken. So next is the relationship between frequency and period. So what I'll be showing you guys is the equation used in this condition. F equals to 1 over t, where F equals to frequency and t equals to period. So basically, we'll need to have the data of t first to find F. So next, I'll be showing you guys this example, an easy one. Given 20 oscillation in 25 seconds. First, we try to find period. The formula is t equals to 25 over 20, 1.25 seconds. Or in other words, 1.25 seconds is needed to complete one oscillation. While frequency is equals to 1 over t, 1 over 1.25 equals to 0.8 Hz. Or in other words, 0.8 Hz of oscillation took in 1 second. So as I promised you guys, I'll be showing you guys where amplitude is located in displacement time graph. So we can look here. Here is amplitude from y equals to 0 to up here, the maximum amplitude. And here, from peak to peak is the period of this oscillation. So moving on, here is the question 1 for this oscillation subtopics. We'll look at A. Find the amplitude, period, frequency for the vibrating system. So first, amplitude. Amplitude is here from 0 to the peak, which is 10 cm. And period, we can look from peak to peak, which is 0.5 to 0.1 to 0.5. So when 0.5 minus 0.1, it equals to 0.4 seconds. So the frequency we cannot get from the graph, but we can use the equation that we have learned before, which is F equals to 1 over t, 10 equals to 0.4 over 0.4 is equals to 2.5 Hz. It's very easy. So next, B. What is the displacement of the object at t equals to 0.3 seconds? The amplitude is equals to 10 cm. So the displacement at 0.3 seconds is equals to negative 10 cm. Just refer the graph. Next is sketch in the same axis a graph of a wave which the frequency and amplitude are half of the wave in the figure below. So when we divided the frequency and amplitude of the wave, hence we will get this red graph. Why? Because the value has been cut into half. So the amplitude has changed, the period has changed, the frequency has changed. So next is damping. So damping, what I can say is when the system loses its energy. Okay, so we'll go one by one. There are two types of damping, which is the first one is internal damping. Internal damping is an oscillating system loses energy to overcome frictional force or air resistance that act on it. While external damping is an oscillating system loses energy due to extension and compression of the molecules in the system. So basically, to summarize these two definitions, they both loses energy. However, the way that they loses energy is different. Internal damping, they loses energy due to the frictional force or air resistance, which is the outside force applied on it. Okay, while external damping is energy loss due to the inside molecule, extension and compression of molecule in the system itself. So that's the difference. The applied force outside for internal damping and the extension and compression molecules in the system. Okay, so I'll move to resonance. Resonance, we have learned on damping just now. So now resonance is the continuous of damping. How? Let me tell you. When external force must apply to the system to enable oscillation continuously, the external force is called force oscillation. And that force oscillation, if the frequency of the external force is equal to the natural frequency of the system will oscillate with maximum amplitude. This is named resonance. To summarize this definition, basically resonance is when external force is applied on that system and the frequency of that applied force reach the natural frequency of the system, hence resonance will occur. Okay, and now we will look into the examples of resonance. The first one is opera singer breaks a wine glass. Yeah, you've always heard of this. Is this real or not? Yes, it is, definitely, by the effect of resonance. Second one is Tacoma Narrow Bridge in USA collapsed in 1940 due to the effect of resonance. How? The frequency of that applied force reached the natural frequency of that bridge system, hence it collapsed. Next is a moving bus produces excessive noise at certain speed when the frequency of engine is equal to the natural frequency of the bus. Yes, easy to understand. And lastly, resonance is used to tune radio or television to your favorite channel. So basically, this resonance system is used in radio and television to adjust the frequency to reach certain frequency in order for us to change the channel. Thank you. Okay, now we'll be learning on types of wave. Okay, there are two types of wave. The first one is longitudinal wave and the second one is transverse wave. what are the differences? I'll be showing you guys after this. So a longitudinal wave is a wave where the particles of the medium vibrate in a direction that is parallel to the direction of the wave motion. How? Okay, let us see this graph below. See, the vibration of the particles move from right to left. It is parallel to the direction of the wave of motion, meaning this is the vibration of particles right to left. The direction of energy transverse is also to the right. It's parallel, it's the same direction. Example is sound wave. Next is transverse wave. So what is the meaning of transverse wave? Wave where the particles of the medium vibrate in a direction that is perpendicular to the direction of wave motion. We'll look at this graph below. So the direction of energy is from here to right, while the vibration of the particles is up and down. It's perpendicular. So the examples are light wave, ripple, and radio wave. So right now we'll be comparing displacement time graph and displacement distance graph. So what are the differences between these two graphs? So basically the difference are the information that we can get from the graph. Okay, so the first one, if you look at the displacement against distance graph, if from crest to crest or peak to peak, we can get lambda. However, in displacement against time graph, we can get the period of the wave of the system from peak to peak or crest to crest. Okay, here we can get amplitude, and here we can also get amplitude. So basically, amplitude in both graphs are the same. Okay, so right now we'll look into reflection. So first we look at this diagram on the right side of this page. The incident wave coming and then reflected onto the plane, and then reflected wave turns out. This is for a plane wave. For a circular wave, it's the same thing, source, and it reflected back to the wall, and then the reflected wave come out. In reflection of plane wave, the angle of incident is equals to angle of reflections, means the angle does not change. Hence, when angle does not change, the wavelength, the speed, and the frequency also remain unchanged. The only changes happens here is the direction. Okay, same goes to here. In circular wave, the distance of source is equals to distance of image, which means the wavelength, speed, and frequency remain unchanged. However, the direction change. Okay, now we'll look into reflection of sound and light. Okay, here it's given here the sound of the clock move into a tube, and then there's a board, it reflected on a board, and then the wave reflected back into the same tube to the ear. This is an example reflection of sound. And in the middle, it's angle of incident. Okay, so this is another example on the right side of this page. This is reflection of light. Okay, so light ray is directed towards the mirror. Okay, from here to there, it produces angle of incident, and then the ray reflected back from the mirror, producing angle of reflection. Okay, So the path of reflected ray is marked on the paper here. Okay. This diagram shows that the angle of incident is equal to the angle of reflected ray. Okay, right now we have seen the theory of reflection of light, how it works. Here we can show you where does all this reflection of light is applied. Number one is side mirror and rear view mirror of a car. So if we usually drive cars, we can see the back of our blind spot, using the side mirror. Because why? Light reflected into the mirror our eye and into the eyes. Okay. So and then we have some others like cat eye reflector, telecommunication, optical fiber, endoscope in medication, periscope in submarine. This is the famous one, periscope, where lights reflected so that people can see the above water view from the inside of the water. Yes, and headlamp of a car. Okay, now we'll look into refraction. So what is the meaning of refraction? So given here, refraction is the bending of the direction of the wave as it travels from one medium to the next, meaning wave travels from one type of medium to another type of medium. This bending is brought about by a change in the speed of the wave. The change in speed is caused by the change in density of the media. So to summarize, the definition of refraction is: refraction is when wave travel from one medium of a different density to another medium of a different density, hence the speed of the wave changes. Okay, that's what refraction means basically. Okay, below here we can see the type of refraction where we will look on to further next. The first one is refraction of light, second is refraction of water, and lastly refraction of sound. Okay, now we'll look into refraction of water. So refraction of water plays with deep region and shallow region. So if water passes through a shallow region or of convex shape, the wave will be convex. Okay, so remember, when water passes from deep region to a shallow region, then it will converge. If water passes through a shallow region of concave shape, the wave will be diverged. So when water flow from deep region into a concave shape of a shallow region, then it will be diverged. Okay, next is refraction of light. So what is refraction of light? This is the example that we can show you. So when light travels from one medium to another different density, as I told you, here is the light ray, and then it travels into a different density of medium. Hence, the speed will change. Okay, so the speed of light is higher in a medium of less density as compared with one higher density. Okay, so speed is faster in medium of less density. The change in velocity of light when it travels from one media to another of different density results in the diffraction phenomenon. Yeah, that's what we basically talk about. It changes density, hence the speed changes and diffraction occur. Okay, and also from chapter 5, light, refraction of light obey the law of refraction where sine r times sine r equals to constant. Okay, moving on, refraction of sound. So refraction of sound, carbon dioxide is denser than air. Okay, here is an example. Okay, we put carbon dioxide in the middle, inside a balloon in the middle, and then we turn on the speaker. Okay, and then the wave will be refracted. Okay, without balloon, the wave has lower amplitude compared to with balloon. Yeah. as you can see, the result, balloon act as a biconvex lens. Yeah. So meaning to say, this balloon act as biconvex lens and converge the wave. Meaning it will from here it move, it will be converged, and then it moves. And then here is another example where refraction of sound also occur, but we changes the gas inside the balloon. Here we use helium. Okay, so this is the difference. Without balloon, the amplitude is higher compared to with balloon. Why? Because wave is diverged this time. Okay, this is another example of refraction of sound. At night, the air closer to the ground is cooler than the air further from the ground. Sound wave travels slower in cool air. As a result, sound wave is reflected in the path of curves towards the ground instead of spreading to a wider area. Okay, so at night, cool air is on the ground and warmer air is on the upper side of the space. Hence, the sound travels refracted like this. It's almost like it bends upward. Yeah, something like that. Okay. Next is the diffraction. Diffraction is the spreading of a wave when it travels to an opening or a small obstacle. So characteristic of diffracted wave, which means after diffracted occur, what happens? Wavelength does not change, frequency does not change, speed of diffractors does not change, amplitude of the wave decreases. So this is the example of diffraction. Okay, the magnitude of diffraction depends on wavelength and size of opening. Okay, so here we can see this is a small this is a small wavelength compared to this. This is a larger wavelength with the same opening. However, the diffracted wave is different. Yeah. See, shorter wavelength, the wave spreads to a smaller area. Longer wavelength, the wave spreads to a wider area. Okay, this is about the opening. When bigger opening, the wave spreads to a smaller area. Smaller opening, the wave spreads to a wider area. Okay. Next is interference, principle of superposition. Okay, so basically, to sum up what it says here, okay, we can see here there are two waves moving towards each other. So this is before superposition. Okay, this is when they met, and this is after superposition. Okay, here we can see the peak, the amplitude of that wave is higher. Okay, so same goes to the right side of this page. We can see one wave have a positive peak, and this one have a negative peak, and then when it meets during superposition, there is no wave. After superposition, it turns back to normal. So that is all from me. Thank you.